developer for the past 13 years. He has worked for several organizations in different roles, such as consulting engineering, government agencies, semi-government agencies, software companies, EPCs, transmission tower design corporations, research universities, and air pollution modeling and monitoring in the U.S. and Canada. This range of experience has given Ravi unique insight into how each of these entities function and what internal processes and bottlenecks one can run into when completing projects under deadlines and with multidisciplinary collaboration required. Quick reminder before we start, all attendees are muted by default, so if you have any questions or comments, please type them in the questions tab. Tomorrow you will receive an email with directions on how to watch a recording of this webinar. For those who are professional engineers, you may request a certificate of attendance that may be applied to your PDH quota, depending on your local laws. Please email me at aaron.hoppel@intergraph.com to request a certificate of attendance after today's webinar. And with that, I am going to pass it over to Jeff.
Well, thank you, Aaron. Today we're going to cover, of course, the topic of pipe bridges using tubular steel, which after yesterday's activity at the White House turning on a couple of pipelines are very actually timely, although we did set this topic a while ago. But while structural engineering software today is very good at crunching the numbers, doing the things like applying and distributing loads, running analysis, optimizing a member size, it's still the responsibility of the engineer to create and design the proper structural system for the job at hand. And material selection and the geometric configuration of the structural system are two items that greatly affect the way loads and forces are distributed throughout the system. Engineering experience gives us a good idea of our starting point, but a good workflow helps us to quickly identify where modification is required and gets us to an efficient design quickly. Today, Ravi will be showing us a workflow in GT Strudel that allows you to rapidly generate those ASCE7 loads and the hundreds of load combinations required by code, optimize member sizes, not in a nilly-willy one-off way, but in a way that realizes the economy of repetition, and also review the results of your analysis. So without any further ado, I'd like to introduce Ravi Ozarker, your presenter for today.
Thank you, Jeff. Thank you, Aaron. First of all, Aaron, can you see my screen?
I can. Looks great.
Okay, perfect. Thank you very much.
You're welcome.
Okay, welcome everyone to the GT Strudel Steel Pipe Bridge Modeling Analysis and Design presentation. My name is Ravi Ozarker, and today I'm going to show you basically how to model these simple bridges in GT Strudel using the current code. Now, this is actually based on a project that I had worked on. What I realized by working on these projects is the codes are extremely complex, and people are in the mode of going in and changing member sizes using very sophisticated software to select member sizes and so on. But here we are going to focus on not just the member selection aspect, but we're also going to focus on how we can pay attention to the structural system and then optimize the structure that way. Okay? Okay, so the agenda for today's presentation is, first of all, I'm just going to introduce GT Strudel. That's the product that I'll be using to demonstrate this whole process. Then I'm going to talk about pipe bridges in general, and then we'll look at a live demonstration of building this geometry from scratch, taking it from modeling analysis to the final design, and at the end we'll have we'll open the floor to any questions or comments. Okay? Okay, first of all, this presentation is about pipe bridges, but GT Strudel is a general-purpose structural analysis and design tool that's well integrated with modeling packages like Smart 3D frameworks and so on. It's also used to design steel and concrete frames that supports AIC 14th edition code. And by that, I mean it also supports the nonlinear analysis requirements for that code. It supports other international codes such as the IS Indian codes, Canadian codes, Euro codes, nuclear codes, and so on. This software is also used in the nuclear world because it has advanced features such as advanced dynamic analysis and so on. Because of the user-friendly environment, GT Strudel can be used to model any type of structures, such as buildings, bridges, oil and gas facilities, towers, stadiums, tanks, and most of these are shown to you in this slide. There's also load generators like moving load generators, floor load generators. A seismic response spectrum analysis can be done. If you wanted to do a time history analysis, you can do that as well. There's a wind load generator also in GT Strudel that can generate wind loads as per ASC 705 code. You can use this product to design offshore structures and do wave loading on them. I also did a presentation about modular design, but you can also do staged construction analysis or modular construction analysis in GT Strudel. Moving on to the pipe bridges, this is a picture of how a standard pipe bridge looks like, and in the background you see how I have modeled that in GT Strudel. Okay. So pipe bridge basically is there to connect two facilities, let's say, or to run a pipeline over an existing roadway or a railway, or something that cannot be moved. Okay, so in this case, it's actually moving over. It's spanning over a freeway. Now, the challenges that we have seen designing these bridges is, first of all, it's a simple frame. But at the same time, we have to design this properly, okay? So with that comes the complexity that the codes bring in. So for example, if you're using the ISC 14th edition code, hey, you have to do notional loads, you have to do property reduction, nonlinear analysis, then you have to go with ASC E7, apply wind along X, wind along Z, wind along 45, same with seismic. You combine that with the notional loads, and you end up with like 700 load combinations to design a simple frame like this. Okay, but at the end, what we think is with the engineer working on this project basically loses a sense of what's a governing load case. Have I really selected the sizes to begin with to perform a full-fledged nonlinear analysis? Is it really going to work with even the dead load applied or the self-weight applied? So those types of calls need to be made before you jump on to complex analysis, and I'm going to show you the whole process and how this can easily allow you to get to the solution without spending time reviewing results for 700 load combinations at the beginning. The other thing is the project that I was working on was a feed front-end design project where we had to generate results quickly. Okay, so we didn't have a lot of budget on those projects, but we need to come up with the quantity of the steel. We don't have any loading, so we got to do these things fast, and with that we need a good software to do that also. So these are the traditional design tasks that everyone might be aware of by now. First of all, you got to model the structure. Now, the model can come from products like Smart 3D, but in a feed project, you may be lucky if you are getting that kind of information. But then in those cases, you need to rely on the graphics for the analysis product to generate your geometry. Then you got to go in and assign some properties based on your experience, some support specifications. You assign loadings, then you move on to analysis. Now, you can do that analysis. Then you assign design parameters, and you optimize, and you reach the final design. Now, a lot of engineers think that this can be all be done in one shot, but sadly that's not the case. Okay, this has to be broken down. So that's my suggested design tasks slide that I'm showing you. What we need to do is what we could do is we could model the structure. Now there might be ways to just model a part of the structure rather than model the entire geometry exactly. Now, when you assign member support specifications, you can assign simple load support conditions rather than applying springs and so on that you don't have any information for. Okay. Then the third one is loadings. You can pick certain governing load combinations or load cases that you think are going to govern in certain conditions. Okay, so for example, if it's a project that's in California, okay, you have to look at seismic. If it's in a high wind zone like Texas, Georgia, you have to look at wind. So analysis, first cut through the analysis. We would actually use the linear static analysis to come up with a force distribution, because nonlinear analysis is going to take some time to produce results, and you got to go in and review if there is any instabilities and so on. If the structural geometry is not passing with linear static analysis, what's the point in doing a nonlinear analysis? And then we move on to analysis design parameters. We would assign minimal design parameters like the yield strength of steel that you want, unbraced lengths, and and those types of detailed parameters would be taken care of later. Then we move on to optimization. Now, this is the place where the experience comes into play. You would pick sizes that you think are going to work, and also look at the availability of those sections and compatibility of those sections with the connections that you're going to provide. Okay, we're going to look at what is the load path, why is the structure failing, and how can we provide a better structural system to make the members pass. Okay. When you also want to look at what is the structure being built for, at what stage. If you're early on in the project, you don't want your members to be at a design ratio of 1.0 because you're not sure of the loadings at that point. So what a corporation might do is just say, okay, let's stick with 0.7 design ratio or unity ratio for our braces or connections to make our connection designs more simpler. And then we would go with the final design to do the estimation of steel and so on. Okay, so all these tasks I'm actually going to demonstrate to you using our product called GT Strudel. Okay, so first thing is I'm going to launch GT Strudel. And GT Strudel is, as I said, a general-purpose structural analysis and design tool. You can generate geometries using any of these options. You can use the CAD modeler to model your structure. You can use GT menu, which is the graphic for GT Strudel. You can use the model wizard to generate your geometry as well. Okay. So before we dive into this, I'm going to pause for a few minutes and let Erin take some poll questions. Erin?
Hey, Ravi. Sure, that sounds great. So let me go ahead and launch this first poll. So if you are using GT Strudel, we're wondering which version of GT Strudel are you currently using? So we have version 33, which is 2014 or prior, version 2015, version 2016, 2016 R1, or 2016 R2. And I'll just wait here for a few more seconds, let everyone get their votes in. I'll count down from 5. So 5, 4, 3, 2, 1. I'll go ahead and close the poll and share the results. So it looks like most are on 2014 or prior, with the next on 2016 R2, our latest version. So.
Perfect. Thank you, Erin.
You're welcome.
So in this case, I'm going to use version R2, and this way you can actually see what that version is all about too. So the first thing that I'm going to do is I'm going to use the model wizard to create the bridge geometry. Okay, so if I double click on model wizard, it opens up a dialog box that shows you all the different types of geometries that you can create. I'm going to click on bridge truss. Now, this model wizard is not just going to create a stick line model of the structure, but it's actually going to allow you to apply loadings, member specifications, you can assign properties and so on. Okay. If I click on next, first thing that it's asking me is, hey, what do you want your joint and member numbers to start off with? Okay, I'm just going to say 1, units of feet and kips. Click on next. The next task is to define how your bridge is going to look like. So I'm just going to use the second option, and it generates a basic frame for me, and I can go in and modify that frame. Now, in this case, I want to create a 200-foot long bridge. So if every span is about 10 feet, I'm just going to say 20 divisions, and it quickly creates a geometry for me. The height of that bridge is about 10 feet. Click on next. The next thing is to define some initial member properties. Okay, so this is where judgment comes into play. For the bottom chords, I'm just going to click on these 3 dots. It opens up the GT Strudel profile browser, in which you see not only the U.S. section profiles, but you also see international profiles like Euro, British, Indian, and so on. But I'm going to use the 14th edition code to design this structure. If I click on rectangular HSS sections, it opens up a big database of HSS sections, but you can go in and filter those sections also here. If I wanted HSS 14, I can filter it down to HSS 14 sections, and the section that I'm going to look for is HSS 14 by 10 by 1/4. Okay, so that's a 1/4 inch, and we're just going to say okay. What that does is it copies that section there, okay, in this dialog box. I'm just going to copy this section and assign it to the top chord as well. So both top chord and the bottom chords have the same profile. For the diagonals, I'm going to use, again, HSS, let's say 6 by 6 by 1/8. That's the section that I want to use. And then it gives you an option to assign self-weight to all members. I'm going to take care of that later. Okay, so let's click on next. I'm not going to release any members because this is a welded bridge geometry. And again, no loadings being applied, although you have these options available to you. Once you click on finish, it creates the bridge geometry for you, and then you can visualize that bridge geometry using GT Strudel's graphical engine, which is GT Menu. Okay, so this is the graphical user interface for GT Strudel, and let me introduce that to you first. Okay, this is a menu-driven interface, as the name implies. At the top we have menus that you need to fill out going from left to right. There's just some important icons being shown in the toolbar. Center of your screen is the graphics window, and on the right hand side you see the data area, which is in which you're going to see data inputs related to the menu item that you click. Okay? Now, the first thing that we should notice is if I show you an isometric view of this frame, it's a planar frame. Okay, so we obviously need to make this a 3D frame. So what I'm going to do is I'm going to use GT Strudel's extrude command to create a 3D frame out of this 2D frame that we have created. Okay, so if we click on edit, extrude model, on the right hand side in the data area, you see inputs related to the extrude command. Okay, so I'm just going to select all members to be extruded. The direction for extrusion is going to be along the Z direction. Now this is referring to the global coordinate system, and I'm going to give, say, one extrusion at 15 feet. That's calculated based on two 24-inch lines running on this bridge. Then I'm just going to go to extrude selected joints. Now what that does is it not only copies this frame along the Z-axis, but it also connects the dots. The pink dots that you see are going to be connected with members. And you have the option to assign a profile to those connecting beams too. Okay? So here I'm going to pick 6 by 6 by 1/8 for the connecting beams. And once you've given those inputs and you say generate extrusion, it shows you a preview. Now this is a preview because if I go in and render it, it just renders one side of the structure. And if you are not okay with that, you can make changes, and once you have an acceptable geometry, you can just say, okay, store it, and it generates the whole geometry for you. Okay? Now that you've created your frame, and made it more complicated, what I suggest is you try to organize the model early on before it starts becoming messy, okay? So for example, the things that I would do is try to form some logical groups and views that you're going to be using to review your results or make modifications, okay? So for example, let's say if I go to views, I go to more options, I can supply a global plane along the XZ, and let's say you know, there's two pipelines that are running on the bottom chord of this bridge, and I want to specify a group of members that are going to carry those pipes, okay? And those groups are going to be used to load the structure and also you know, design them. So let's go in, we'll just say, okay, I want to create a XZ plane view. If I say create new view, all I need to do is just click on a dot, and what it does is it selects a global plane, okay? Let's say cancel, I want an XZ. Okay, so this is the option that I want to choose. XZ, if I say click on one dot, it basically creates a deck view for me, and it's called view number 5, okay? Now, the other way you can organize this model is using groups. So if I go to create model, click on create groups, add new, I can just say, okay, the group name is pipe support, let's say support number 1, okay, click on OK, and you can start adding members that you want to be included in this group, okay? So let's say I'm just going to pick randomly any members. Now this would actually come from the piping isometric drawings and so on, to figure out, you know, exactly where you're going to be supporting your pipes if it's running across this bridge, okay? So I'm just going to pick these beams in a random fashion. Then I'm going to add a new group, and the good thing about GT Strudel is it doesn't forget the previous selection, okay? So we have the previous selection there in the graphics. I'm just going to create another group for specifying the pipe supports for my second pipe. If I say OK, members, I can pick you know, the remaining members that I want that are going to support the second pipe, okay? Now once you've done that, you can review those inputs, okay? So for example, I wanted to know what beams are included in this pipe support 1 group. I just say display members, and it shows me where those members are. If I go click on pipe support 2, it shows me that those members are included in that group, okay? So you would form a group of chords, beams, braces, top chord, bottom chord, and that'll help you out to organize the model, and it'll help you out later when you are reviewing the results and, you know, even designing the structure, okay? So let's move on. We'll just see an isometric view of the structure. Now, what you also want to do is, say, if you want to communicate with other engineers, okay, you can go in and quickly create a GTS file for review. Okay, so if I go to File, Generate GT Strudel File, you can generate a text input file, okay, and specify the location where that file is going to be stored. Okay, so I'm just going to say pipe bridge. Okay, so that's the name that I'm going to give. And if you save that, this file is a simple text file that can be emailed to any person who has GT Strudel, and they can basically open it up in one shot. It contains all your groups, all your changes that you've made to the model. Okay. The other good thing is, like, you can use this file to document things. Say, for example, the engineer who worked on it and who made the changes. So it's a good communication tool rather than dealing with just binary. And I'll show you the advantages of that. Okay, so let me close this file. Let me close this dialog box. Now, what we have done so far in this presentation is we have tackled modeling. We have modeled some members, support conditions using the wizard. We also now have to go in and apply some loadings and load combinations. Now, the tip that I had suggested is we are not going to model like 700 load combinations, but we're going to first see if a few basic load combinations would work. Okay, so in this case I'm going to create 3 load cases: dead load, wind load, and live load. I'm going to create 1 notional load just to show you how that notional load can be created using the graphics, and then I'm going to create 2 more load combinations. Okay, and after that we'll run a static analysis and see how the structure performs. Okay, so moving on, we are in the GT Strudel interface again. We're going to go to modeling self-weight. Now, first thing that we want to do is obviously self-weight. Okay, so we're going to say dead load. What that does is it uses the density of the steel, the profiles that you've assigned, to generate self-weight on all members. Okay. Next task is to generate, let's say, the wind load. So we're going to use wind load generator. We're going to use ASCE 705 load combination. Load generator. So I'm just going to say wind load along X. We can give a description, wind along X. We can give the wind speed. So I'm just going to say 100 miles per hour wind. Let's say it's blowing at an angle of 90 degrees, which is the X direction. We're going to accept these defaults. I'm just going to say, okay, the topographic factors are 1. Let's say the exposed surface area, I'm just going to pick 2,000 and add 100 also as the added force area. Moving on, we'll just go to member wind load data. Now, you can actually go in and load the entire bridge using this wind load generator, or you can pick members to which the load needs to be applied, okay, or even frames to which the load has to be applied. In this case, I'm just going to apply it to the entire frame, and then the next task is to specify what classification as per ASCE 7 does this fall into. I'm just going to say lattice framework. Now, here it's going to use the profile that we have assigned to this structure to come up with the wind loading. Okay, so we're going to use this table option. Now, a lot of these structures in the petrochemical world or in the oil and gas world are, I mean, you might have a pipeline that's actually carrying flammable liquids or gases. Okay, so in that case, your pipe bridges need to be insulated. So I'm just going to say, okay, I have an insulation provided for this, and I'm going to say 0.0625 as the insulation thickness. And then we can say, okay, I want the KZ factor to be 1, the CF factor to be 1, and once you've provided all those inputs, you can click on Add to Member and Save Load, and that actually creates the wind loading on the frame. Okay, so that's wind load along the X direction. Now, let's say we want to go in and provide the the deck loading. So now the deck loading, let's say, is going to be designed for 100 pounds per square feet loading. I'm just going to say new loading, call it live load, and give it a name. The direction of the loading is going to be global Y. We can go in and again select a joint on the deck, and GT Strudel will go in and automatically pick all the members that actually form the deck. Okay, so here we go. We click on these 3 dots. We just click on one point, okay, on the bridge deck. If we click on OK, provide a load value and do a 2-way load distribution, it automatically goes in and shows you a load distribution diagram, and once that's done, it generates the live load on the structure. Okay. Okay, so far we have created the primary load cases. Of course, if you're using the AISC 14th edition code now, you have to concentrate on how to generate notional loads. So we have that feature inside GT Strudel. We can go to modeling, and if we go to loads, there is an option to form notional loads. Okay, so I can just say, okay, I want notional load to be applied along the X direction also, and we're going to use apply it along the X with a factor of 0.003. We're going to use the dead load to generate our notional load, and if we click on Add and Form Loads, that actually forms the notional loads for us. Okay. Now comes the task of providing the load combinations. Now, in reality, no one's going to define 700 load combinations using the graphics. Okay, you might have a seed file that does it. Okay, I'm going to do that later. But for demonstration's sake, I'm going to generate a load combination for you. If I go to loads and just say form new loading, I'm just going to call this load combination 101, and let's say this is going to be 1.2 self-weight plus 1.6 live load. Okay, so when I say 1.2 self-weight, it also includes the notional load, and I'm going to specify a factor of 1.2 for it. And for the live load, we're going to specify a factor of, we have programmed in these values too, so we can just say, okay, 1.6 times live load. Once that's done, we have created our first load combo. Okay, so let's create our second load combo, which is load case 102. Again, this is going to be 0.9 times dead load plus wind load along X direction. Okay, so here we're going to pick a factor of 0.9 for the dead load, and for the wind load along X, let's just say 1. Okay, and once you add that, that creates your second load combination. Now we have defined our loadings. Now we're ready for our analysis, and we're ready to see what this structure is, how the structure is going to perform. Okay, so let's go into analyze. As I said, we're not going to dive into nonlinear analysis because there's no point in doing that if it doesn't even pass with linear static analysis. Okay, so we're going to analysis, static analysis. It just takes like 0 seconds to come up with a force distribution for that frame. We go into steel design. Now we start defining some design parameters. Okay, so we go into, we pick the AISC 14th edition code, as I said before, and then we go in and we, there's a lot of design parameters, as you can see, but we can go in and just change the grade of the steel. we're going to pick A992 as the grade of the steel and assign it to all members and click on OK. Now comes the show time. What we'll do is we'll go to Steel Design, and if we click on Check Members, all members, here are the results, okay? Now guess what? The ones with the asterisk are the ones that are failing, okay? And now we clearly know that it's 102, so it's probably the wind load that's actually causing problems for the entire frame, okay? Now if we go to the graphical modeling, here you can visualize the design results, okay? If we go, first of all, let me show you the load generation, okay? So if you go wind load along X direction and draw arrows, these are all the wind loads that have been generated, live loads. If you wanted to see, these are the live loads that assigned to the bottom chord, and so on. You can see results like deformed shapes. This is live. This is wind. You can sort of animate it. If you wanted to study it more. But if you wanted to see the design results, you can go to Results, Steel Check Code, and you can say Select, and the members that are shown in red are members that are failing. Okay, now let's review what the actual ratios are also for this frame. So if I say, okay, I want to see a color-coded diagram of all the code check results, you can see that some of these are actually failing pretty badly. We have a design ratio of like unity ratio of 6.2 for some of these members, okay? Okay, so what we need to do is modify the frame, okay? So first of all, what I would do is, modify, there's several ways you can modify it, okay? So let me exit out first. Let me exit out of this, file if I wanted to do that, not save any changes. But if we come back to the PowerPoint, okay, now we have done this. We are going to pick some sizes. We're going to study the load path to provide a better structural system and finally make it pass, okay? So first of all, let me go into the file that I had generated, okay? So this is the text input file that we had generated, okay? So if I go and find, you can open it using any editor. I have opened it using Notepad, and here you see we have assigned, a member property, let's say 14 by 10 by 1/4, okay? So in the design world, you want to basically backtrack where you started off from also, okay? So for example, in this case, what I could do is I could put in a comment that says, okay, this is my initial section, okay? And you can just say, okay, now if I wanted to modify it, let's say I want to modify it to HSS 20 by 12 by 5/8, okay? You can do that, okay? Now the same thing applies for the HSS. Let's say we wanted to change all the sections here in this input file from HSS 6 by 6 by 1/8 to, let's say, 8 by 8 by let's say 3/8. Okay, so by experience or based on availability of the sections, if your boss says, okay, hey, Robbie, just try these sections out and see if those work. We have some surplus material on the site. We want to make use of it. Let's do that. Okay, so once you do that, you've also documented what you've done. You can put in your date, your initials, and that maintains your design history. Okay. Now, if I come back into GT Strudel and I open up that same file, which is C:temp, and let's say this is the one that I had modified, 1040 Central Time. If I click on Open, it'll show me the modified shapes. If I go to Modeling, Graphical Interface, you should be able to see those changes if I go to select member only and click on that member. Now the size has been updated to 20 by 12 by 5/8. Okay. Now you must be thinking, oh wow, I need to make all those changes through the editor. No. I was just trying to show you one way of modifying the structural geometry. You can also use the graphics to do the same thing. Okay, for example, like if I wanted to change the size, I can double click here in this row and I can just say, okay, change with similar values, and I can change it in this dialog box as well. Okay, I can just add new, pick any section and do those changes. It'll change all the HSS 20 by 12 by 5/8 to whatever section that you choose, okay? Okay, so we have generated this geometry so far. What we also need to do, we have modified the section sizes. Now what we need to do is make some modifications to the structural system, okay? So let's first concentrate on the bottom chord. We knew that the wind was causing an issue, right? So what we can do is we can start creating some logical groups to make modifications as we did. Okay, so for example, let's say global plane along the XZ. Create new view. Let's just concentrate on this bottom deck level and start drawing some bracing members. Okay, so easy. We can go to create, menu, place members, tools, and we can pick a size that we need to assign for our braces. We can just release those because those are smaller braces, and we just have to go in and connect the dots. Okay, so it's very easy to make modifications in the graphics as well as you saw in the editor. Okay, so once you've done that, you can repeat the same process for the top chord. I can just say, okay, I want to create a view for the top chord members, and here I'm just going to place a similar type of bracing pattern at the top level. Okay, just to minimize the deflection that we have been getting due to the excessive wind loading. Okay, so we have made modifications to the entire frame. We have changed member profiles. Now we need to do the real analysis. Okay, so the file is called pipebridge.gti, and what I'm going to do is exit out of GT menu and close this. Now you can go in and generate loads and load cases and load combinations using a seed file. Okay, when you start a project, you can set up a seed file, and that's the file that you keep on using over and over again to generate your load cases and load combinations. Okay, but what I'm saying in this presentation is sometimes that's too much information early on when you don't know that the structure is going to pass with linear static analysis, okay? But now we've taken care of those problems. Now we want to do a real analysis. What I have done is I have written an Excel macro that'll generate these combinations for you, okay? Now this Excel macro, Aaron is actually going to distribute it to you all after the presentation. You can download it and you can test it out. What it does is it's an Excel spreadsheet which asks you, okay, where are you going to store all your GT Strudel, this particular model. So I'm just going to go to C:temp to specify that directory location, okay? Next thing is, okay, what is the GT Strudel file that you are trying to use to create your load combination? So let's say, you know that it's C:temp. This is the file, pipebridge.gti modified 1044 AM. It is 1045 right now. So if I click on open, it copies the path here. Then, do you want to create notional loads? Yes, I want to create notional loads. what is the notional load factor? I'm just going to say 0.003. And once you've done that, okay, what is the wind load that you want to use for your structure? I'm just going to say 100 miles per hour wind. Give these default parameters, and with a click of a button, it creates all the primary load cases. Now, by that I mean it's actually creating self-weight, the piping loads. It's also creating the wind load along X, wind load along Z. So there's a lot of load cases being generated in the background, okay, which is based on your feed file that you might be using at your company, okay. Next task is the load combinations, okay. So this is where it's going to generate, the 600 plus load combos. So if I click on Create ASD Load Combinations, it creates those load combinations for you. Now, let's go back and see what has happened, okay? So if I go to command mode and open up this file, this is a file that it actually creates with a timestamp, okay? It doesn't modify your original file, but it creates a copy of your file because, you don't want your original file to be to have any errors if that was the case. So if it creates a copy for you, if you click on open, this time not only do you see the primary load cases, but these are all the load combos, believe me or not, 700, almost 600 load combinations created using this tool, okay? Now we have a real model, okay? Now we proceed with, we know that the structure could perform well with the nonlinear analysis. Let's test that out, okay? So we go to analysis. This time we do the nonlinear analysis, or the second order analysis that's required per the code. We just go to geometric nonlinearity and say that we want to apply it to the whole structure, and then we go to analysis, nonlinear analysis, and solution parameters. We're going to run 10 iterations, okay? So you got to really appreciate how much GT Strudel is doing at this point. It is actually running about 600 load cases. It's going to run multiple iterations for you, or nonlinear iterations if you say okay. Yes, it does take some time to process those results, but it's a lot of information, okay? So looking at this, at the early on, when you're actually doing the preliminary design of the structure, this is too much information, okay, to comprehend. So once you know that the nonlinear analysis has been done, then you can go in and go to steel design, assign your parameters, like your, let's say what we had done in the previous case was, okay, we wanted to go in and assign A992 as the steel grade for all members. Once you've done that, we would go in and design all members also, okay? Now again, it's actually checking each and every member for every single load combination, and it's also checking it at different points along the section. Okay, so there's a lot of computations going on behind the scenes, and that's why you can see that the speed, I mean, it takes some, it's actually taking some time to process those results. But at this point, it's okay because we know we are actually converging to a design solution, and there's going to be minimal changes at this point, so we can go back to modeling GT menu, and there's our 3D frame. Let's review the design results. If we go to results, steel code check, select members. Hey, everything's passing now. You have almost designed a bridge structure, 200-foot bridge span structure in almost an hour. We can go and look at the allowable ratios, and I mean in a color-coded format. And if we do that, we can see that, yeah, we do have some members hitting a ratio of 1.0 But then at that point, it's an engineering judgment as to do you find these results acceptable? Do you want to push them down to like another unity ratio? Okay, so that's what I wanted to show you, and with the live demonstration. My concluding comments for today's presentation is that, okay, we can easily model structures using these software products, but we need to have a process in place. Of course, we need a good user interface to make these changes also like we did. We also recommend that when you make changes to member sizes, yes, if there is a product that does member selection for you, GT Strudel actually can select member sizes for you. But you need to pay attention to the applicability of that section to your design. So, for example, is that section even available on site, or would it interfere with any existing piping? You have to pay attention to the load path. For example, what's causing the structure to fail, and then modify the structural system so that it'll pass. And when you reach that stage, then is a good point to proceed with the complicated analysis or the nonlinear analysis, assign notional loads, material property reduction factors, see deflections, and so on. Okay? So Erin has some poll questions before we wrap up.
Yes, I do, and I just want to do a quick reminder. If you have any questions, to go ahead and enter those into the questions tab, and we will be answering those pretty quickly. So right now I have a poll question for you guys. Have you ever needed to do AISC 14th edition code direct analysis for any of your projects? Just a simple yes or no. 14th edition code direct analysis for any of your projects. Just a simple yes or no. And I'll go ahead and count down from 5. So 5, 4, 3, 2, 1. And I'll go ahead and close the poll and share the results. So fairly split, yes and no. People being able to use 57% yes, 43% no.
Excellent.
We have a few follow-up questions as well. So let me. Do you believe automation of loads and load combination generations will save a significant time in your workflow? So as you guys are working through these things, to some of the tips that Ravi showed you, would those help? Answer is yes or no, and I'll just wait a few more seconds, count down from 5. So 5, 4, 3, 2, 1. I'll go ahead and close and share. Overwhelmingly yes, so that's great news.
Perfect. Yeah.
And yeah, last question on the ballot. How much engineering time do you think this would save you over the way you do this type of project now? So specifically looking at how Ravi did his presentation today. 25%, 50%, 75%, or I don't currently use the AISC 14th edition code. 25%, 50%, 75%, or I don't currently use the AISC 14th edition code. And I'll go ahead and count down from 5 again. So 5, 4, 3, 2, 1. Go ahead and close the poll and share those results. So 39% would save about a quarter of the time, 24% save half the time, 11% saving 75%, and then another quarter, 26% says I don't currently use the AISC 14th edition code. And then another quarter,
Perfect. Thank you.
Okay. Yeah, that's all of the poll questions that we have for you guys. Ravi, we have a few questions for you.
Okay.
One is your spreadsheet creating the seed file you refer to? Is that correct?
Yeah, the seed file is something that you can create yourself. Like it's a simple text file that you can generate whenever you start a new project. You use that as a template to start off with, rather than starting fresh. So that spreadsheet is actually programmed to automatically generate that. Based on whatever load combinations the AISC and the ASC 7 recommends. Now every company has their own naming conventions for dead loads, live loads, and notional loads. So this may or may not work for you, but I just wanted to show you that that's one way to do it.
Yeah, no, very good.
Yeah.
We have a question as well about wind load commands. Are those available in only version 2016 R2? And I believe that is correct. Is that right?
Correct,
That
yeah.
wind loads
Yeah.
is a new feature. We've added that in our 2016 R2 edition. So if you don't have that current one and you would like to use wind loads, then please speak with your dealer or sales representative to kind of get that updated. Let's see. Does GT Strudel warn you that the analysis section and the design section are the same? I'm not sure. Do you know what that question is, Robbie?
Analysis and design section are not the same, or are the same?
Does it warn you that they are the same?
Yeah, I didn't
You
get that
take
question.
that question offline. That's all right.
Yeah,
No,
okay.
we'll follow up with you personally, John. No problem.
Okay.
See, we have a lot of good jobs, and they want to see the webinar again. So great job, Ravi.
Thank you.
Let's see. How do you consider wind load due to pipes? Would that be possible in GT Strudel?
Wind load on pipes is, usually people would use Caesar to design their piping. We usually used to, the company that I used to work for, they used to use Caesar to generate the piping loads, and they used to give us the piping wind loads also. But in absence of that, we had design guides to generate these wind loads. So GT Strudel does not do the piping automatic load generation on piping, but you can certainly get that loading from other sources and apply it to your structure. The danger with that is, if you model a pipe inside GT Strudel, you're actually relying on the stiffness of the pipe. So the pipe is actually carrying the bridge, so that's the problem.
Yep.
So the pipe is actually carrying the bridge, so that's the problem.